Hello, everyone, and welcome to today's broadcast, Treasure, Optimizing Titration Electrodes and Consumables, presented by Jessica McVeigh, Technical Support Specialist, Metrome, and Lori Spafford, Product Manager for Titration, Metrome. I'm Alexis Cross of LabRoots, and I will be your moderator for today's event. We are delighted to bring you this educational web seminar presented by LabRoots and sponsored by Metrome USA. Metrome offers a complete line of analytical laboratory and process systems for titration, ion chromatography, electrochemistry, and spectroscopy. From routine moisture analysis to sophisticated anion and cation quantification, Metrome can help you develop your method and configure the optimum system. For more information about our sponsor, visit www.metrome.com. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. Just click on the Ask a Question box located on the far left of your screen and type your questions into the drop-down box that appears on the screen. Our speakers will respond to your questions via email. If you have trouble seeing or hearing the presentation, please click on the Ask a Question box to let us know that you're having a problem. This presentation is educational and thus offers continuing education credits. Please click on the Continuing Education Credits tab located in the top right corner of the presentation window and follow the process to obtain your credits. Today's webcast will be available for on-demand viewing through January of 2019. You will receive an email from LabRoots letting you know when this webcast will be available for replay. Please join me in welcoming Jessica McVeigh and Lori Spafford. I will now turn the presentation over to them.
We're going to be talking about optimizing titration electrodes and really kind of trying to put some parameters around, do we trash it, or do we need to replace it, or do we keep it and repair it? So let's go ahead and get started. So I kind of like to start this discussion out by saying, we all have that junk drawer, right? Either at home or at your desk, or maybe sometimes it's in the lab. And it's that kind of that safe place where we like to stash things if we're unsure if we're going to need it again and just really aren't ready to part with it. When it comes to replacing titration or pH electrodes, we often uncover a bad habit of simply just adding the retired electrode to a drawer full of the used devices. And so, here we're going to ask, why do we insist on hanging on to the electrodes long after we've replaced them? Sometimes it has to do with uncertainty, right? We're just not exactly sure how to troubleshoot it or really what to focus on when it comes to electrode health. Sometimes it's a matter of really just needing to optimize resources in the lab. So unless that glass breaks, we're just going to deal with the symptoms of maybe a slowing response or a noisy signal, when deep down we probably know that that electrode has been in use long past its lifetime. And then sometimes there's a possibility that, well, maybe I can pull this electrode back out of the drawer sometimes and use it as a backup if something goes wrong. And so in today's session, we're going to work through some of those reasonings and hopefully provide you with a better thought pathway to understanding how to diagnose your electrode better. We'll add some clarity around best practices for maintenance and care as well. Then I'm going to pass our session over to Jessica McVeigh. Her focus here at Metrome, like Trevor said, is providing support. So day in and day out, she's taking calls and emails, helping labs troubleshoot and making recommendations. And so through her experience, she's developed 5 simple ways to know when to replace your electrode. And then lastly, maybe you have a drawer full of those electrodes and you're just not sure how to dispose of them. So we'll wrap up the session today with a couple of additional resources, and one of them will be how to go about making that disposable in a responsible manner. So let's get to it. Part of understanding how to troubleshoot means you need to know how the electrode works. Even if you've been in the lab for years, this section will be helpful. We often take for granted the workings of just a simple electrode. And while titration and pH measurements aren't complex per se, getting a refresher of this knowledge always helps us create a clear pathway when we start to think about diagnosing the system. So let's start with the dictionary definition, right? When we're talking potentiometry, we're using an electrode that produces a voltage that is logarithmically dependent on the concentration of a selected ion. okay? We're talking about ISEs here, whether that's a pH electrode or other ion-selective sensor, common examples being fluoride, chloride, copper, lead, and even surfactant ion-selective electrodes. Other sensors are redox electrodes and maybe a metal ring combination electrode, commonly constructed of silver or platinum. So all of these are electrodes that give us a voltage that's dependent on a concentration of a substance in our sample, okay? So ground level. If we look at what is needed to make the measurement, the same 4 components are needed to complete the circuit for every sample, or every example rather. So we need 2 measuring sensors. We need an indicator or measuring electrode that gives the potential dependent on the composition of the sample solution, okay? The other is a reference electrode. So this will supply a constant potential, which is as independent as possible from the sample solution, okay? Next, we'll need a meter or other device to collect that signal and convert it into something that makes sense to us. And then lastly, we've got to have a sample to complete that full circuit. More commonly today, we see combined electrode systems. And this is really because it's more convenient to have both components built into a single sensor. It takes up a lot less space in our sample and is less dependent on sample homogenization and simply reduces the surface area exposed to the sample. This means we basically have less to worry about in regards to cross-contamination as we move from sample to sample. So after this session, you may go back into the lab and wonder, what type of electrode system do I have? Simply look to see if you have a glass bulb and a fill port. Those are the easiest telltale signs of a combination electrode system. Now, if you call in for support and you end up getting Jessica on the phone, we're likely going to start asking questions about the electrode first. And there are some common terms used to navigate the different sections of the electrode, and knowing these will help you get to the cause fastest. Okay, so since it's most common, we're going to be talking about the combination electrode now. The general parts of the sensor are the electrode head, and this is where the electronic connections are made, and definitely an area we want to protect from getting wet with sample or titration reagents. Following it down, next we have the fill port or a refill opening. So the reference electrode system needs constant care and feeding with electrolyte solution, and this is where we access that. The shaft, or glass shaft, or sometimes plastic, depending on the type of electrode, is just the main body of the electrode. And while we want to keep this area and below rinsed of the sample between measurements, there's no actual measurement or any magic happening here, right? But give yours a look in the lab. Get familiar with how it's supposed to look when it's healthy. That way, if it does endure any cracks, you'll know how to see those right away, because those will affect how the electrode works. Lastly is the electrode tip. This is the sensitive measuring area of the electrode, basically where the important stuff happens. The electrode tip is composed of the diaphragm, which is part of the reference electrode, and the glass membrane or bulb, which is the actual sample, where the actual sample measurements occur. In application instructions or general discussions, you may be asked, hey, is the tip of the electrode submerged? That means this entire area. So this is the portion of the electrode that must be in contact with the sample throughout the measurement or the titration. Now, because of the importance of each of those, that membrane and diaphragm, we're going to go one level deeper with each of those portions. So the image you see on your screen now is a cross-section of the membrane bulb. So again, this is the ion-sensitive part of the electrode. The membrane is constructed of special glass, and this is the area in the image where you see the silicate skeleton that contains kind of the lithium ions and among other things floating around in there, okay? On either side of that glass, there are 2 very thin gel-like hydration layers. So in your image, those are the gray kind of half moon shapes. So thinking about the outer hydration layer, this is what actually comes into contact with our sample solution, while the inner layer comes into contact with the electrolyte solution. So when the electrode comes into contact with a sample solution, H+ ions are either diffused into or out of the gel layer, leaving behind a charge. So think, for example, just maybe on the right-hand side, we're looking at an alkaline example. So in that solution, the H+ ions diffuse out of the gel layer and a negative charge is left on the outer side layer of the gel, that hydration layer. Since the glass electrode has an internal buffer and that has a constant pH value, the potential at the inner surface of the membrane remains constant during the measurement. So bringing it full circle, we're able to get the total membrane potential as a result of the difference between the inner and the outer charges. So electrode, membrane, or bulb, we've got that now, how it's working. Now, after this session, you may go and look in that infamous electrode drawer and notice that not all of the bulbs look alike. That's actually on purpose. The membrane can be made of different types of specialty glass to help improve performance in certain types of samples. So just like you would use a different sample container for a non-aqueous sample versus, say, something just like water, different glass material is more optimal depending on the sample type. The easiest way you can tell that there's difference or something going on is just to look at the color of the glass. So you see the images on the left-hand side of your screen. That gives you some examples. So blue, some is clear, some is yellow. You also may notice that sometimes they have different shapes. So this is a simple way to make sure that we can get the entire electrode design into the sample. So on the right, you'll see some different designs. So the top one is kind of a needle or a taper design. And this is really helpful if you've got semi-solid or thicker, kind of more viscous samples. So think yogurt or a soft cheese or something. You may also run into an application where you don't have a lot of sample. You still need to make these measurements. For that, there is a microcylinder. This bulb measures only 3 millimeters across. And this really small electrode only requires 20 millimeters of immersion depth. So depending on what your sample cup looks like, this can be very, very small. The last one on your screen is interesting because the entire sensor's measuring surfaces are actually on the bottom. So this means that only the bottom needs to be in contact with the sample to take a pH measurement. So here we see this design being helpful for applications where we're looking at maybe a pH measurement of a textile or a leather fabric, or even making pH measurements on skin. So, all right, let's shift gears back to the reference electrode and take a closer look at what's happening with the diaphragm. So the diaphragm, just in general, is responsible for providing a constant outflow of the electrolyte into the sample. That means the electrolyte must go into the sample solution. We want that inner electrolyte solution to slowly drain into the sample as we're making measurements. It obviously will be draining so slow that you don't see it with the human eye, but it will be leaving the electrode. This happens due to simple hydrostatic gravity-driven pressure. So the only way this occurs is if that fill port is open. So write that down. During measurement, you must unplug the fill port at the top of the electrode. Remember, the measuring circuit we talked about earlier, if you don't open the fill port, you're not allowing that circuit to be completed by allowing that electrolyte to flow. So if we focus at the image on your screen, you'll see a couple scenarios to help us understand the importance of keeping the electrolyte solution topped off. So if we focus on side A, here, this is what happens when we let the electrolyte level drain to very low levels. When we put that electrode into the sample solution, the pressure on the outside of the electrode is greater than the pressure on the inside. So what happens is we have the sample creep, follow that red arrow, creep up into the inside of the electrode. And then what happens is we are contaminating the reference chamber and ruining the electrode beyond repair here. Looking at side B, simply keeping the electrolyte solution topped off allows the solution to be flowing in the right direction. So that yellow arrow, we want that one to be bigger. We want the electrolyte to be flowing out. So really the take home here is Keeping the electrolyte filled up properly is key to not only a properly working electrode, but also preventing damage. Just like the membrane bulb, you may notice a couple of different designs for the diaphragm. The ceramic pin may be considered a little bit more of an older generation, so that's the electrode image on the left. You see a very tiny red circle around that pin diaphragm. For the most part, the fixed ground joint, or the electrode to the right, is more commonly what you'll see. So the diaphragm is the actual entire frosted section kind of in the middle there. So that entire, it goes all the way around the electrode. That's where the electrolyte will drain into the sample. Regardless of design here, the functions are the same. We want to slowly ensure contact between the sample and the reference electrode via the electrolyte solution. When it comes to using them, the only difference you'll need to understand is the impact of stirring, and that's the graph on your screen. If we put both of these electrodes into a stirring sample and watch the signal, we see a fairly steady response, okay? Once we shut the stirring off, you can see the ground joint diaphragm maintains a steady signal while the ceramic pin starts to trail off. This comes down to just an ergonomics. So the ceramic pin is on one side of the electrode, and so that causes a little bit of change in how that signal is picked up. All that is really important to know here is that when it comes to construction of the diaphragm, the ground joint offers a really good solution that's less dependent on stirring. Okay, so if we keep moving here by taking a look at the pH scale and really consider for a moment what we're asking of these electrodes. So you'll see on the left the standard pH scale that ranges from 0 to 14. On the right, you'll see what pH measurement means in terms of the concentration of H+ ions. So you'll notice at very high pHs, there are very few H+ ions in the solution. Basically, this becomes very difficult range to measure pH in. Since our pH electrode, you should basically think of it as an ion-sensitive electrode for H+ ions. Okay. A few slides back, we talked about all of the H+ ion exchange and potential generation that is occurring at the glass bulb or the membrane. As we get into samples of higher pH values, we run into what is called the alkali error range. In strongly alkaline solutions, standard electrode may give measurement errors due to the potential contribution of other alkali ions, so think potassium, sodium, lithium. When we get into these higher pH values, there are so few H+ ions in the solution that not only does the pH get difficult to measure, but we've got those other +1 ions contributing. So rather than an ideal straight linear relationship across the pH measuring range, pH values can appear to be lower. So the key to kind of ensuring that you're getting accurate results in this scenario is to make sure you're using an electrode with a membrane designed to handle these pH ranges. If you're working in this sample range, check the color of the membrane glass. Natrium's electrodes are infused with ions to give the bulb characteristics to withstand these difficult samples. So in this instance, yellow glass is designed to perform well in these high pH scenarios. Next up, let's talk a little bit about calibration and why it's needed. So think of this simple image on your screen now as a 2-point calibration. So we have 2 buffers, give 2 potentials, that's your U1 and U2, at 2 pH values, pH1 and pH2. So going back to the beginning, the potential of a measuring electrode can always only be given relative to that of the reference electrode. So in order to compare the systems, the electrode 0 point, something that we define as 0 millivolts, for pH 7, we need to use that. And also we use the electrode slope, which is given to us through the Nernst equation. And that is just theoretically defined as 59 millivolts per 1 pH unit. Now, remember those are ideal values and they'll change as a result of the aging glass membrane or a change in the diaphragm system. So for this reason, a pH meter or device, whatever you're making the calibration or pH measurements with, must be adapted to the characteristics of the electrode. So when we calibrate, we're not actually making any changes to the electrode per se. We're adapting the system to the electrode conditions. So all of this to say, make sure we're calibrating at regular intervals and using fresh buffer solutions. You often hear when you talk about pH, temperature comes up. And it's not important to have the entire Nernst equation memorized here. You might earn some bonus points though. But I think we can break it down more simply. Basically what you need to know is that temperature influences the pH value. If an electrode is calibrated at 25 C, then it should be capable of a linear measurement throughout the whole pH range and provide correct results. However, it is the electrode is used, if the electrode is used at a different temperature, the electrode slope will change and possibly the electrode 0 point. So on your screen now we see a sample. If you look at the blue line, so the ideal sample measured at 25 C, if we take that same measurement and say it's chilled down, we'll get, you can see the shift from either side there. One of the results of the calibration is the electrode 0 point. Sometimes you may hear this referred to as pH 0, intercept, or the asymmetry potential. Essentially what we're looking at here is, so we've got that theoretical 0 millivolt reading at a pH of 7. In the real world, we would make an adjustment from that theoretical value, and that is the asymmetry potential. General calibration recommendations. Use a 3-point or 3-buffer calibration. And when you're selecting buffers to make your calibration, select ones that bracket the pH range of the samples that you're measuring. It's important to use fresh buffers, especially in the higher concentration ranges. Anything over pH 9 will start to absorb CO2, and that will alter the value. And then lastly, make sure we're selecting the right buffer in the instrument and either enter that temperature measurement manually or set it to automatic or continuous for temperature correction. So to maximizing the life of your electrode, there are a few tips that I'd like to share with you that can help improve the electrode life. Between measurements, titrations, and when you're first putting the electrode into use, you should always rinse the electrode first with distilled or GI water. If that's not enough to clean it properly, say you're working with a really difficult sample, you can use a detergent or solvent depending on the kind of contamination. After that, always rinse it again with that distilled or GI water in order to recondition that electrode. The conditioning time can also depend on the cleaning time. So depending on what you cleaned it with, like say if you used a solvent, that means you've likely stripped away that hydration layer on the membrane, and we need to allow it to condition in water a little bit longer. It's also very important to avoid, as much as you can bear, wiping the glass membrane with a tissue. A lot of times I know we like to try to get that last drop off of the bulb, or we feel like we could really get it clean, it'll do better. But in reality, this practice can actually cause mechanical micro damages, which can change the property of the electrode. So micro scratches in the membrane can manifest as a noisy signal from your electrode. Also, you can load the electrode electrostatically, and once you've charged the electrode, it can be very difficult to regenerate it. So try as much as possible to avoid that. If you need to clean the electrode, you know, I've got a couple kind of buckets here for us. So routine cleaning really consists of periodically emptying the electrolyte from the electrode. Just use a plastic dropper and kind of suck the electrolyte out of that fill port. Go ahead and rinse the chamber with fresh electrolyte. Never fill this body with water. You don't want to put water in there. I know logic tells us, oh, it's salty in there, and I know water will just dissolve those crystals and rip them right out, but this is actually a really horrible practice for the reference sac that's in there. So even if it takes a couple of passes, fill it and empty it, and then fill it and empty it again. In the end, always refill and store the electrode with electrolyte. With the deep cleaning, this may be required if the diaphragm has become clogged, and the electrode may require a deeper cleaning. So, I mean, if you've got a sample that might have wicked up into that frosted glass area of the electrode, this might be helpful. So what you're going to do here is empty the electrolyte out of the body of the electrode and place the sensor into a cleaning solution overnight. Let it sit overnight. The cleaning solution will have kind of wicked up into that diaphragm, but not up into the chamber. The next day, fill the chamber with the proper electrolyte solution and leave the spill port open. So we want the electrolyte to drain and completely flush that diaphragm back out. When it comes to selecting a cleaning solution, that will really depend on what your contaminant is, what you're working with. For example, if you have silver precipitates, those typically respond really well to a 7% thiourea and 0.1 molar HCl cleaning solution. If you're dealing with some really stubborn protein deposits, we can remove those with a 1% pepsin in 0.1 molar HCl. For fats and oils, simply use a suitable solvent. So try something like IPA. If that works, you may have to go with toluene or xylene or something. So here a quick word on electrode storage. For me, kind of the rule of thumb here is just to think about the two parts of the electrode and how they want to be stored, right? So you have the membrane and the diaphragm. It always comes down to how those need to be cared for. The membrane, what's key here is that it really just can't dry out. So ideally, it would love to be stored in distilled water. If we separately think about the diaphragm, this is a really concentrated salt solution inside of there. And so ideally, it would love to be stored in reference electrolyte. Well, we can't do both here, right? So the key answer here is to get that perfect balance, and that's found in just simple electrode storage solution. So this formula is specially designed to quench both of those. So we provide enough hydration for the glass bulb and enough salt to keep the diaphragm moving. Additionally, it has some added antifungal properties, and this will help prevent algae growth and contamination if the electrode is stored for extended periods of time. We often get the question, well, why can't I just store it in my KCl electrolyte solution? So the graph on your screen now will really help you understand and explain why we don't recommend this. If you focus on the blue line, this represents a pH measurement taken using an electrode that was stored in KCl fill solution. Excuse me. So what we see is that the potassium ions have taken up residence in the electrode membrane, and it took up to the 1,000 second mark. So we're looking at just over 15 minutes here for those K+ ions to leave the membrane and allow us to get to an equilibrated pH measurement. The red line represents the measurement taken from an electrode that was stored in buffered the electrode storage solution. So you see the pH measurement response is very quick and it's very stable. So really the take-home message here is keep your electrode in storage solution, especially for those overnight storages, and you'll be immediately ready to make measurements the next day. If you're sitting there listening now and cringing a little bit because you've been storing your electrode in KCl, don't fret. You really here will just need some front-end conditioning time to make sure that you're getting a steady and accurate signal. So get that electrode bulb stirring in water to let it refresh, and then from here on out, let's look at using an electrode storage solution. If you're not entirely sure what electrolyte storage and cleaning solutions, it's all just kind of a little bit, it's a lot of information right now. This fit kit can be very helpful. So this will get you off the ground and provide a good, healthy first step, ensuring your electrodes have that proper care and feeding. So next up, I'd like to pass the session over to our technical expert, Jessica McVeigh. She has 5 simple tips to share with you. Jessica?
Hi, everyone. As Lori mentioned earlier in the beginning of the presentation, it may be hard to let go of some of your electrodes. However, I'm here to help. I have 5 simple tips to determine when it's time to let go and dispose of your old electrodes. Okay. Number 1, check response time. The response for each pH unit should be about 60 millivolts. If you start at pH 7, if you notice the millivolt reading for pH 7 should ideally be 0 millivolts with plus or minus 15, as Lori mentioned before. Each pH unit higher than 7 will decrease by about 60 millivolts, and each pH unit lower than 7 will increase by about 60 millivolts. So as you can see here, pH 4 is ideally around 180 millivolts, and pH 9 is ideally around negative 120 millivolts. The voltage is measured after 3 minutes in a stirred solution and is used as a comparison value for determining the response time. The response time is the time after which the measured voltage has reached this comparison value within plus or minus 1 millivolt reading. The maximum permitted response time of the pH electrode is about 60 seconds. If the response time exceeds 60 seconds, you may want to consider replacing your electrode. Number 2, check the potential offset. If you're experiencing results that are off, whether they're higher or lower than normal, or they're beginning to shift, consider testing your electrode's potential offset. This is the difference of your electrode is measuring versus the ideal millivolt reading of a buffer. First, perform the millivolt measure of pH 7 buffer. Next, evaluate. Is your measurement within the offset limits? Depending on the type of electrode you're working with, you may have different offset limits. You may also measure the potential difference between pH 7 buffer and the pH 4 buffer. Just repeat the previous procedure to determine the millivolt measurement for pH 4. Determine the difference between pH 7 millivolt reading and the pH 4 millivolt reading. Consider replacing the electrode if the difference is considerably higher or lower than 150 millivolts. Okay. Thirdly, check the calibration slope. Remember, a good calibration slope is necessary to correlating the correct pH value to the millivolt signal of the electrode. If you're uncertain if your electrode is past retirement, perform a quick calibration and take a look at the calibration slope. Consider replacing your electrode if your slope is consistently lower than 95% or higher than 103%. To refer to the slope after calibration with the touch control, it can be found in the calibration data of your particular sensor. In Tiamo, you can find the slope is listed in the Sensors window of the Configuration tab. Number 4, check drift and streaming potential. Drift is a signal change in a stirred solution over a period of time. We usually recommend 3 minutes. The streaming potential is the difference of measured signals in a stirred solution versus a non-stirred solution. For each electrode status, I've listed the maximum permitted drift in a stirred solution and the maximum streaming potential. Consider electrode replacement if you're observing a drift of greater than 3 millivolts per minute and a streaming potential greater than 4 millivolts per minute. Number 5, inspect regularly. We heard earlier how important the membrane and diaphragm are making accurate measurements. I would encourage you to get familiar with these key parts of your electrode. Pull them out and inspect them. Ensure there aren't any cracks. It's good practice to inspect them before every time you use them. Here we see an electrode that has been put away with the fill port plug open and not in the storage solution. What we end up with is an electrode with a reference system that is completely non-functional. You can try to revive it by rinsing the outside with warm water, empty and flush the inside of the electrode with the electrolyte fill solution. And remember, do not use water, and store the electrode overnight in the storage solution. After all this, I would still recommend going back and performing a calibration check to verify that it was permanently damaged. Hopefully these tips will help you determine when your electrode needs replacement. And as in a summary, understanding how electrodes work always allows you to perform better inspection and understand important calibration results. Simple electrode check and calibration tests can reveal the health of the electrode and quickly indicate if replacement is needed. And finally, depending on usage and care, common to replace electrode every 6 months to 1 year of use. So Lori's got a few more things to go over before we finish with the Q&A, so I'm going to go ahead and hand it back over to her. Thank you.
Thank you, Jessica. So because there are some electrical components in the electrode head, we often get asked if we can help ensure responsible disposal of exhausted electrodes. So for that, I'm happy to say that we can help. If you have old electrodes and you need to dispose of them and you want to ensure that it's being done responsibly, you can ship them to us and we're happy to take care of them. The only thing I'll ask is that just ensure that you've emptied the electrode solution from the body, and please address the shipment to Metrum USA Electrode Disposal Program. You can package and ship the item to the address on your screen. Lastly, if you need more information, if you'd like a little bit more informative session or you want that direct access to some of our experts, we're going to continue to extend our Below the Surface seminar series with 4 more dates in all new locations. So if you head out to seminars.metrumusa.com, you'll be able to access the registration for this free event. So now I'd like to hand it back to our moderator for the live Q&A session.
Excellent. Thank you very much. And for those of you who may have joined us late, if you have any questions for Lori or Jessica, you can ask them simply by typing your query into the question box, which is located at the bottom left-hand side of your screen. So the first question that I have for you is, how often do we need to replace our pH electrodes?
Yeah, so, this is one of those questions that's always, we get asked it a lot, and Jessica kind of summed it up for us as a general rule of thumb, to not be shocked if you need to replace your electrode every 6 to 12 months. All of this, of course, is depending on how it's cared for, how many measurements you're making. I mean, we have some locations that are making hundreds of measurements a day and some that make a few a month. So usage will play a lot into that replacement factor, as well as how you're able to care for it.
Excellent. Thank you. Now, how is the electrode pH measuring capability changed by storing it in water? So for that, really the reason why we say to stay away from storing it in water is because what you're going to do is end up drawing the electrolyte out of the reference system. So that salt-saturated solution would love to be dissolved in water. So what you're going to do is really just put more wear on that reference system. Okay? Excellent. Now, what did you mean by the electrolyte level being too low? Do you mean below the sample level?
Yeah, that's exactly right. I don't know if it's helpful to jump back out to that slide where we were having that discussion. So I believe this was the slide we were looking at, and
Yes, so the image on the left where we're in section A, that the sample, once the electrode is submerged into the sample, that would mean the sample volume is actually higher than where the electrolyte volume is in the electrode. So you're on the right track with that. So definitely keep it filled higher to avoid that contamination.
Excellent, thank you. Now our next question asks, is it okay to dry the tip of the electrode with a Kim wipe after rinsing with distilled water?
No, we really try to get people not to do that. So sometimes I know that we fear that extra drip hanging on the bulb is going to somehow dilute our next sample or dilute our next measurement. Really, if you could just give it kind of just a tap, just a light tap with your finger to knock that drop off, that's really best practices. Chem wipes can have a lot of static or be very harsh when they come in contact with the membrane. So as best we can, try not to do that. I know there are some customers out there, or some folks out there listening now that say, hey, listen, I cannot, I've got to keep this clean and my samples are just really, really difficult. So we can definitely try to work with you to help come up with an alternate, solution. Just overall, really try to avoid that.
Excellent, thank you. Now our next question asks, would it be better to warm or cool buffers to a similar temperature of the sample, or warm the electrode in the sample and use room temperature buffers?
Can you repeat that question for me?
Sure. Would it be better to warm or cool buffers to a similar temperature of the sample, or warm the electrode in the sample and use room temperature buffers?
Okay, so when it comes to temperature, what we want to do is to measure the buffers at room temperature. We don't want to heat anything, either side, electrodes or buffers per se. What we want to do is, with your buffers, there will be a calibration table or a buffer table with temperatures. So we need to tell the system what temperature we plan to perform the calibrations at. So that's kind of where we're going to go with that. The rule, kind of the general rule of thumb, is that we'd like to make sure that our calibration temperature and our sample temperatures are in alignment. If you're using a pH electrode with a built-in temperature sensor, this is really the most convenient. So it will automatically, continuously make sure that that temperature adjustment is made in the pH value that we report back out. So hopefully that was helpful.
Yes, thank you. Now, the next question asks, does both the tip and diaphragm need to be submerged in the sample to get an effective reading, or just the tip?
We recommend here that you do need the tip and the diaphragm submerged into your buffer or sample at the time of measurement. So the answer would be yes, the diaphragm and the bulb.
Excellent. Now, our next question has to do with routine cleaning. Do you recommend that be done once a week or once a month? Is there a recommendation there?
Yeah, I mean, so again, this is really going to come down to how much are you using it. If you're doing a lot of measurements, multiple, let's say, if you're making more than 10 measurements a day, and that electrode is in high use, it's probably a good idea to make sure that you're at least inspecting it to make sure that it doesn't need to be cleaned. When we look at the routine cleaning of exchanging that electrolyte, what we're doing there is preventing the electrolyte concentration inside of the chamber from increasing. So we often see if we begin to see it salt out, that means that the electrolyte concentration inside is changing, and we need to keep that system as steady as possible. So keep an eye on those things once per week, and if you find that maybe you can go every other week, that would also be appropriate.
Excellent, thank you. Now, our next question has to do with storage recommendations, and why are long-term storage recommendations, why do they differ from short-term storage for metal probes?
So on this one, we're talking specifically about metal probes. So if you've got an electrode that is basically two metal sheets, so think no reference electrolyte solution. This is something that we can store dry. So those metal surfaces don't need any contact with moisture or reference electrode. So this is going to be something that you would use maybe in a vitamin C application. So think Radox, two platinum sheet tip electrodes. On the flip side, we could have a metal electrode that has a metal ring and has a reference solution. So this would be kind of a combination system. That electrode needs to be stored in reference solution. So right here, the only factor that we have to take care of here is ensuring the reference doesn't dry out. Again, that metal ring doesn't need any particular attention. And then we have a third scenario where you have a metal ring electrode that has a glass bulb. Now, in those configurations and that type of a sensor, the glass bulb is what we have to consider storing. So just like your pH measurement, your pH electrodes, that bulb needs to stay hydrated. Again, disregard the metal. Metal does not care if it's stored dry or whatnot. That electrode you would store in water. So hopefully I didn't add any to the confusion, but if there's follow-up questions, we're happy to continue to the discussion after the live session.
Excellent, thank you. Now, our next question has to do with calibrating, and how often do you recommend calibration?
We recommend calibrating every day that you're using your pH meter and your electrode. If you're not using it for the day, you won't have to bother calibrating it, but if you are using your electrode that day, we do recommend calibrating it, just for a pH measurement. If you're titrating, then you won't really need to calibrate your pH electrode. However, if you are having problems with your titration, we do recommend performing a calibration in regards to troubleshooting your electrode.
Excellent, thank you. Now, our next question asks, are there any checks I can do for my platinum and silver ring electrodes?
Yeah, so I believe that is one of the resources that is attached to this session. So there is an application bulletin there that walks you through how to perform an electrode check for those metal electrodes. So great question. Go out to that resources tab and download that information.
Excellent, thank you. Now our next question says, how often or how do you know when to empty the electrode and not just top it off, or the electrolyte and not just top it off?
Sure. So when it comes down to that, I guess when you're in everyday use, if you continue to just top it off, that's something that you really should just give it a peek every day and just have a squirt bottle beside there and top it off on the daily. If it has been left open for an extended period of time, so if the still port was left open overnight or maybe over a long weekend or something, you may need to look a little closer and make sure that we haven't developed salt crystals around that top portion or on the inside of the electrode. So once those develop on the inside, we definitely need to go ahead and get those removed and completely empty and refresh it.
Excellent, thank you. Now, can you explain again why storing the electrode in potassium chloride solution is not okay?
Sure. So that slide, I think if I bump out to it, it would be really helpful here. Yeah, I think we're pushing it left here. So here, in this instance, it's not necessarily stirring it in the KCl. We're talking about long-term storage. So if we go back to this one, this is a scenario when the electrode has been kept overnight in a KCl solution. And the reason we don't want to do this is because those potassium ions will take up space in the membrane of the electrode. And in order for us to be up and running quickly, we've got to get those flushed out. So we need the hydrogen ions to be moving back and forth across that membrane, and if the potassium's in the way, we're not going to get a very good accurate measurement. So that's the reason we really avoid keeping the electrodes stored in that KCl solution.